Okay, good afternoon, everyone. So in the last lecture, we have started with the basics of shielding. Shielding is to protect the device from the electromagnetic interferences happening from the neighboring equipments. So you can shield either the source, which is emitting electromagnetic noise into the space, or you can shield your device so as to protect it from the electromagnetic interferences happening from the neighboring equipments. The basics required for understanding of the shielding. We'll quickly go through it. So shielding is nothing but a metallic barrier, a conducting object that we are placing between source and the receptor or emitter and receptor, so as to protect the receptor or receiving device from the electromagnetic noise. So generally the waves are going from free space, which is air, and shielding, which is made up of metal. Then that wave has to pass through the metal to reach to the receiver. So one should know the wave propagation inside a metal and inside a air. Once again, we'll revise the concepts. When electromagnetic waves are passing from a free space, it doesn't get attenuated. The alpha attenuation factor is always 0, and beta is a phase constant, which is omega under root mu 0 epsilon 0. That's why the amplitude of the electric field is just Ex plus. It is not changing or decreasing with change in distance traveled by the wave. And the ratio of amplitude of E to amplitude of H will always gives you impedance, and that impedance indicates the impedance of that medium. If I know E and H in free space, if I take its ratio, I'll get impedance of the free space, and the impedance of the free space is around 377 ohms. However, for good conductor, the conductivity is much higher than the omega epsilon factor. Therefore, the amplitude of the electric field in good conductor case is Ex of Z, that is Ex plus e raised to minus alpha Z into this term. This term indicates the wave is actually time varying in nature, and wave is traveling along positive Z direction. E raised to minus alpha Z term indicates the amplitude of the electric field that is traveling along Z direction is decreasing exponentially by a factor of alpha as a function of distance traveled by the wave Z. So we have discussed the skin depth concept also. What is skin depth concept? Whenever waves are passing in conductor medium, we have to find out the distance traveled by the wave for which the wave amplitude has been reduced to 37% of its maximum amplitude. So this skin depth concept is very important from understanding of shielding concepts, because whenever waves are incidenting on the shield, the current will induce on the shield, and that current, depending on the thickness of the shield, some of the current may appear on the inner side of the shield where your receptor is placed, where your receiving device is placed. So your shielding material should be thick enough so that the current will not penetrate inside the shield, so that the field will not go inside the shield. If your shielding material or shielding barrier, if it is thin enough, then that current can pass through the shield and may appear on this surface also, and that current will produce some magnetic field, and that may affect the receiving device. So if the thickness of the shield is large enough as compared to the skin depth of that conductor, then current will not go on that side of the conductor. Current will be there on the surface or skin part of this conductor on this side only of the shield, where source is there, and the receiver is placed on this side. So receiver will remain safe. The electromagnetic waves are not going on that side. So that way the shielding should be done. So that way skin depth concept is important. Then the attenuation and phase constant offered by the conductor are same, that is under root of pi f mu sigma. The propagation constant gamma or k is given by this factor. The intrinsic impedance of the good conductor medium is j omega mu by sigma under the square root. You can simplify this expression to this. And the gamma propagation constant, you can simplify this in real and imaginary part. You will get alpha and beta to be same, that is under root of pi f mu sigma. So the skin depth is the distance traveled by the wave for which wave amplitude is becoming 0.37. So this is the wave amplitude. Ex plus e raised to minus alpha Z is the amplitude of the wave inside a conductor. So if Z, that is the distance traveled by the wave inside a conductor, if it is equals to 1 upon alpha, the amplitude of the electric field becomes Ex plus into e raised to minus 1. E raised to minus 1 is approximately 0.37. So the amplitude of the electric field that is traveling inside a conducting medium is becoming 0.37 Ex plus when Z is 1 upon alpha. Z is nothing but your delta, and that is nothing but 1 upon alpha. That is nothing but the skin depth. Why it is called as skin depth? Because the depth traveled by the wave inside a conductor is very small. So that current that is flowing inside the conductor due to the induced field inside the sheet will be penetrating the conductor hardly a micrometer to millimeter distance, and because of that the current tends to appear on the surface of the conductor. This skin depth concept is significant especially at high frequency, because when frequency is high, skin depth is low. So current tends to appear on the surface of the conductor, especially at high frequency. At low frequency, current is flowing throughout the conductor cross section area, that you have studied already. So shielding problems are difficult to handle because of deliberate discontinuities that we are adding to facilitate the user with various features. We'll talk about the shielding discontinuity today. Then whenever waves are passing from one medium to other medium, lot of things may happen: reflection, refraction, then internal reflection, absorption. We have discussed those things. So this is the incident wave coming from this side. This wave is coming from free space where your source is there. So this wave is not at all attenuating. This wave is traveling like this, where the first finger is electric field, middle finger is magnetic field, and wave is traveling like this. So when waves are traveling in free space, the amplitude of the wave, that is amplitude of E field and H field, will not decrease, because attenuation of wave in free space is 0. So whatever amplitude of wave is there at this point at the source, where same amplitude of the E and H will appear at this point. This is a second object, which is a conducting object, which is formed by metals, which is a shield. On this side we are having a receiver. So part of this incident wave is getting reflected and remaining is getting transmitted. So this reflected wave should be as high as possible and transmitted wave should be as low as possible. Some part of the incident wave may get penetrated inside the shield, and that transmitted wave goes on attenuating because it is traveling inside a shield, and the amplitude of a wave decreases exponentially inside a conductor. We have studied the skin depth concept by a factor of alpha. Alpha for a conductor is under root of pi f mu sigma, which is very, very high. So the wave that is penetrated inside the metal, the amplitude of the wave goes on decreasing as a distance traveled by the wave inside it. So T is nothing but the thickness of the metal. So when the wave appearing from this point to this point, the amplitude of the wave will decrease abruptly. And part of this wave again is getting reflected because the next medium is again air, where your receiving object is there, receiving device is there. So this is the internally reflected wave. So what part of the wave should reach to the receiver? Ideally speaking, nothing should reach to the receiver. The reflected wave, the absorption that is happening, attenuation of wave that is happening in the conducting material, that is shield, and the internal reflection should be as high as possible so that no signal should reach to the receiver. So the receiver will remain safe. It will be compatible to the electromagnetic environment. So shielding effectiveness depends on the reflection losses, the absorption losses, attenuation losses happening in the shield, and the internal reflection losses. So one can calculate the shielding effectiveness by adding the three losses. These three losses should be as high as possible. Shielding effectiveness should be infinite in ideal case. However, practically it should be as high as possible. So reflection coefficient is nothing but the difference of impedances divided by addition of impedances of the two medium. Transmission coefficient is 1 minus reflection coefficient. So that is 2 into Z2 divided by Z1 plus Z2. While Z1 and Z2 are the impedances of medium 1 and medium 2. Impedances of medium 1 is your air, medium 2 is your metallic barrier. So we have discussed those things. So the shielding effectiveness in terms of power we can calculate 10 log of P1 by P2, where the suffix 1 and 2 indicates the power received at the receiver without shielding, and P2 is the power received at the receiver with shielding. Now if I have a single shield, if I have a source which generates electromagnetic noise, a receiver, and in between them if I'm keeping a single shield, a metallic sheet, a conducting object, what will happen? As only one metallic object is placed, depending on the thickness, if the thickness of that metallic object is large enough, then we may have one internal reflection. So one reflection, one internal reflection, and one absorption. These losses will happen once only. Reflection loss will happen once only, internal reflection will happen once only, and absorption will happen once only, because we have placed only one metallic object, a barrier between the source and receptor. So what is the definition of the reflection loss? Reflection loss is minus 20 log of transmission coefficient. What is transmission coefficient? That is 1 minus reflection coefficient. What is reflection coefficient? Z2 minus Z1 divided by Z2 plus Z1. So you can calculate transmission coefficient, that will comes around 2Z2 by Z1 plus Z2. We have discussed just now, and this is the transmission coefficient expressed in terms of V, where V is nothing but Z1 by Z2. However, this is equals to 2Z2 by Z1 plus Z2 only. But this is written positive, so it has inverted. Log of A by B is minus of log of B by A, right? Similarly, absorption loss is 20 log of 1 minus reflection coefficient into e raised to minus gamma t. What is gamma? Alpha plus j beta. What is alpha and beta for good conductor? They are under root pi f mu sigma. T is nothing but the thickness of the wave. We are talking about internal reflection happening from the shield. So exactly what we are doing over here, whatever signal that is there at the junction of the first metal, this signal is traveling like this, and when the signal is traveling inside a metal, the amplitude of the signal goes on decreasing exponentially. So when this is coming at this point, it finds change in impedance because the next medium is air. So part of this wave, attenuated wave that is appearing at this point, will get reflected and remaining is getting transmitted. So we have to find out the internal reflected wave at this particular point. So this will be dependent on the amplitude of this internally reflected wave depends on the amplitude of the wave that is appearing at this point. And the amplitude of the wave that is appearing at this point has decreased significantly because of the attenuation in the metal. Now, what is the attenuation in the metal? That is e raised to minus alpha t. What is e raised to minus alpha t? Alpha is the attenuation constant inside the conductor, that is under root of pi f mu sigma, and t is nothing but the thickness of the conducting shield. So the wave amplitude, the reflection amplitude has been decreased by e raised to minus alpha t. This term is the phase of the wave. So this is the internally reflected wave, which is 20 log of transmission coefficient only. Transmission coefficient, you can write it as 1 minus reflection coefficient. Please remember, V minus 1 whole square divided by V plus 1 whole square is nothing but your reflection coefficient only. Because if I substitute this V minus 1 whole square divided by V plus 1 whole square, you can simplify further. V minus 1 whole square, I can write it as V minus 1 into V plus 1. V plus 1 whole square, I can write it as V plus 1 into V plus 1. So 1 V plus 1 from the numerator and from the denominator will get cancelled. So what I'll have is V minus 1 divided by V plus 1. And what is V? It is Z1 by Z2. So what I'll get from this, it is Z1 minus Z2 divided by Z1 plus Z2. And that is nothing but reflection coefficient that is happening at the interface between the air and the metal. So that is this particular factor, V minus 1 whole square divided by V plus 1 whole square, that is nothing but the reflection happening at the second interface over here. And this reflection amplitude depends on the amplitude of the wave that is appearing here, over here. And this amplitude is attenuated significantly by the attenuation of the shield. So that attenuation we have considered, e raised to minus alpha t is there. So this is the total internal reflection. And the absorption loss is nothing but alpha t only. That is the attenuation offered by the shield into the thickness of the shield. That is nothing but the absorption loss, attenuation of wave inside the shield. This attenuation loss or absorption loss is generally measured in Nepers per meter. So to convert it into dB, we are simply multiplying it by 8.686. So shielding effectiveness is addition of 3 reflections, that is reflection loss plus absorption loss plus internal reflection loss. This should be as high as possible. So the same concept we can extend it to N shields. To increase the shielding effectiveness, we can increase the number of shields. We can have N number of metallic barriers between source and receiver, so as to protect receiver from electromagnetic interference. So different metallic objects, different conducting objects you can use over here, starting from 1 to N, having different impedances, different conductivity and different thicknesses. So how the internal reflection, the reflection and absorption loss of this particular shielding will vary, we'll discuss. It is very similar to the reflections losses that we have discussed for single conducting shield. So this is 20 log of, this is reflection loss of a N shield material. Reflection loss is 20 log of minus 20 log of transmission coefficient. So you can see over here, this is 20 log of transmission coefficient. Now what is transmission coefficient? For the first barrier, what is the first barrier in this case? Air is there, electromagnetic waves are coming from this region, and then the first metallic object is there. So impedance of the air is eta 0, that is 377 or 120 pi. Impedance of the metal 1, Zm1, let us say, is the impedance of the metal 1, and the eta 0, that is 377, is the impedance of the air. So the transmission happening from the air to the metal 1 is this. You can simplify this. This I can write it as eta 0 plus Zm1 divided by eta 0. So you can rewrite this expression eta 0 plus Zm1 divided by 2 eta 0. 20 log of A by B is minus 20 log of B by A, right? So that means this 2 eta 0 will go to the numerator and divided by eta 0 into eta 0 plus Zm1. So this is a transmission coefficient only, that is 2 eta 0 divided by eta 0 plus Zm1. If it was minus, so this is the transmission coefficient that happening at the first interface, which is this. Similarly, transmission coefficient, that is the wave that is getting transmitted from first metal to second metal, that depends on the impedances of the two metals, Zm1 and Zm2. So this expression has been extended to n elements. So 20 log of 1 plus Zm2 by Zm1 divided by 2, and so on. So this is the transmission coefficient of the nth element or nth metal. The absorption loss, again, it is alpha t, but we have n metals starting from 1 to n. So alpha 1 T1 plus alpha 2 T2 plus alpha 3 T3, and so on till alpha n Tn. The T1, T2, T3, these are the thicknesses of the metal 1, metal 2, metal 3, and so on. And alpha 1, alpha 2, alpha 3 are the attenuation factors of different metals. Attenuation of wave is different in different conducting objects. So if you are using different conducting metals, the attenuation factor will vary. And attenuation in dB can be calculated by multiplying this total attenuation by 8.686. Then the internal reflection is again 20 log of transmission coefficient we have discussed. So this is the transmission coefficient that is happening from the first, that is 1 minus what is V1, reflection coefficient. In this case, please don't get confused with the V that we have discussed earlier. V that we have discussed earlier was the ratio of the impedances. In this case, this V1 is nothing but reflection coefficient that is happening from first interface, reflection coefficient or reflection coefficient happening from the second interface, reflection coefficient happening from the nth interface. I hope you remember the V expression. It was actually for total internal reflection. The expression was this: V minus 1 whole square divided by V plus 1 whole square, and this is nothing but reflection coefficient only. Just now we have discussed this. So instead of writing this big term many a times for n sheets, they have written V1, V2, V3. So this is V1 means reflection happening from the first interface, V2 means reflection happening from the second interface, and so on. So this Vn is nothing but the reflection between the n and n minus 1th interface. So that is the difference of impedances of the last two metals. So it is Zmn minus Zmn minus 1 whole square actually. So one of the bracket will get cancelled with the denominator. So what I'll have is difference of impedances and addition of impedances. That is nothing but a reflection coefficient happening from the nth barrier. So these are nothing but reflection coefficient only. So 1 minus reflection coefficient is transmission coefficient, and this reflection coefficient depends on the amplitude of the wave that is attenuated in that metallic barrier. And at this K1 is nothing but the propagation constant, which is alpha plus J beta. Alpha is different in different medium. So the reflection coefficient amplitude depends on the attenuation of the wave happened in that particular metal. The single internal reflection loss expression, this expression has been extended to n number of barriers metallic sheet. So to improve the shielding, it is recommended to use isolated double shielding approach. So what happens in this case? Two metallic objects are there which are separated by a dry plywood. Dry plywood is assumed to be a low loss dielectric whose conductivity is 0. It's kind of lossless dielectric. That means attenuation offered by this particular medium is 0. This is metallic object of thickness T1, metallic object of thickness T3. Source is there on this side, receiver is there on this side. So obviously the emitted waves has to pass through these three barriers to reach the receiver. So it is difficult to pass through these three barriers. So the device can be protected well using this approach. Again, the three losses they have calculated: absorption loss, the internal reflection loss, and reflection loss. It is very same as of previous case. Absorption loss is attenuation of wave into the length of the conductor alpha 1 T1 plus alpha 2 T2 plus alpha 3 T3. You can multiply it by 8.686 to get it in dB. So this particular dry plywood, which is kind of lossless dielectric, we have assumed, right? So this offers zero attenuation. Lossless dielectric means it is not offering any attenuation. So alpha 2 is not written over here because alpha 2 is 0 if this medium is kind of lossless medium. So the only two expressions are there, alpha 1 T1 plus alpha 2 T2. And the internal reflection, again we can calculate by using the same formula. We can extend it to 3 shading barriers. So here you can see V1 is the reflection coefficient happening from the first interface into e raised to minus 2 K1 T1, where K1 is alpha 1 plus J beta 1. Alpha 1 and beta 1 are same for conductor, that is under root of pi f mu sigma. T1 is the thickness of the sheet. Now for second medium, which is dry plywood, the total reflection that it is written over here is 1 minus reflection happening from the second interface, which is this, into this e raised to minus J 2 beta 2 into T2. So alpha 2 is not there because in plywood amplitude of the wave is not getting attenuated. Absorption is 0. Therefore, alpha is not there in this case. So gamma is just J beta. For third medium, it is extended similarly. Similarly, the reflection loss happening from this double isolated sheet can be extended to same as of the previous expression. The problem with this conducting shield is the conducting shield basically offers low absorption loss as compared to magnetic shield. So instead of electrical conductor, it is recommended to use mu metals, a magnetic material. Mu metals or magnetic materials are those materials whose permeability is very, very high. You can see from this table, the mu metal can have a permeability about 80,000 also. Mu R value is 80,000 over here. Iron is another mu metal kind of magnetic material whose permeability can go to 1000. So these are the materials which has very, very high permeability. So what is the difference between electric conductor shielding and magnetic conductor shielding? The magnetic conductor shielding offers very high absorption loss as compared to electric shielding loss. So we need to reduce the amplitude of the signal as significantly as possible so that the net signal going to the receiver should be as low as possible. So to increase the absorption loss, mu metals are recommended, especially at low frequency. But mu metal again has certain drawbacks. It has a saturation drawback problem is there. So instead of one mu metal, multiple mu metals can be used. So these are the different materials, conducting materials one can use for shielding and different purposes. Then the next part is the shielding discontinuities. As I have told you in the earlier lecture that shielding problems are difficult to handle due to the presence of intentional discontinuities in the shielding walls, such as shielding panel joints, ventilation holes, visual access windows. These are the discontinuities that we are adding deliberately to facilitate the user. When I'm having a perforated shielding with square holes or circular holes, what will happen? The electromagnetic waves from the source may penetrate through that holes where metal is not there. And those holes are basically for ventilations or to see what is happening inside the device, or for heat sink purpose also we can use those holes. So there are many reasons why we are perforating the sheets. So the perforation may decrease the effectiveness of the shielding. So one should take care of those discontinuities. The shielding is greatly affected by the joint surface material finishing. So obviously when we are having two materials crossing each other, we are joining them by using some technique, either by bonding, by electrical welding, by some other methods. So the finishing must be good enough so that the two metals should be made up of same materials, so that the resistance difference will not be there between the two material. Corrosion properties will not change. If I'm using two different dissimilar metals, it may lead to corrosion also, and it may lead to some resistance difference also, and that may again leads to leakage of electromagnetic energy, and that is not desired. So the shielding effectiveness is greatly affected by those things. And also while performing the bonding and welding and other things, due to oxidation and other aging phenomena, the shielding effectiveness can be degraded to a great level. So shielding effectiveness decreases with increase in frequency. Obviously, at high frequency, the radiations are stronger enough so that can penetrate the shield to a greater distance. And again, at the same time, the wave attenuation is directly proportional to frequency. So wave attenuation increase with increase in frequency. So higher the frequency, attenuation of the wave is also high. But when I'm having high frequency radiations, those radiations are strong enough to get penetrated inside an object. So typically, the shielding effectiveness of a commercially available conducting gaskets is in the order of 80 to 100 dB. These gaskets are just to prevent the leakages that is happening at the joints. These are all the gaskets. These gaskets can be made up of the conductors. It can be made up of rubbers. They are basically used to avoid the leakage that is happening from one surface to other surface or from one device to other device. So here, if this gasket was not there, there was a gap. So because of this gap, some leakage of energy may happen from one point to other point. That's why this gasket is placed, which avoids the leakage of the energy and it protects the device from getting damaged from the electromagnetic interference. So these conducting gaskets are basically used to avoid the leakage of the energy happening from the surfaces of the two conductors. So we can see this is the conducting gasket that is placed next to the shield, and this is the shielding panel. So if I am having my EMI source on this side and the victim device, the receiving device is there on this side of the shield, obviously. The source of EMI is, let us say, dipole antenna, which is generating waves like this. Obviously, it is transmitting waves on this side also, similar waves, but we don't have any receiving device on this side, so we are not bothering about this radiation. So this radiation will induce some current into the shield, and that current will go through the shielding panel through the conducting gaskets. And this shielding panel, the two shielding panels that are there on the two sides of this shielding wall, acts like a small dipole antenna, and they again starts radiating similarly. And that radiation will reach to the receiver, and again it will affect the performance of the receiving device. So this is another disadvantage of the gasket. So other discontinuities that are there is, as I have said, for ventilation purposes, we have to perforate the shielding objects. So if the perforated holes, that can be squared holes or circular holes, if the diameter or aperture of that perforated hole is much smaller compared to wavelength, then this is how the E and H field will penetrate through the shield. And if the diameter of the perforated hole inside the shield is large enough, you can see a lot of energy is getting passed from that area where there is no metal, a hole is there on, and that energy can directly damage the receiving device or directly affect the performance of the receiving device. In this case, please remember, the aperture of the perforated hole doesn't affect the shielding effectiveness, but the circumference, the linear dimensions of the aperture is considered, because those linear dimensions of perforated holes actually affects the performance of the shielding. That the linear dimensions of the apertures starts radiating energy, and they resonate at certain frequency depending on the dimensions, linear dimensions of that aperture. So that is just like an antenna only. So if the linear dimensions of the aperture, whether it is a square hole or a circular hole, or if the dimension is comparable to wavelength, then that perforated hole itself can act as a good antenna, and that will radiate lot of energy towards the receiver, and that may damage the receiver. So the shielding effectiveness of such a system is given by 20 log of lambda by 2d, where d is nothing but the diameter of the hole and t is nothing but the thickness of the shield. Then if I have multiple apertures in the shielding barrier, what will happen? A lot of energy may leak through those holes, and that is not desired. The shielding effectiveness depends on the spacing between the two holes, the diameter of the holes, and many other factors are there which decides the shielding effectiveness. So shielding effectiveness for multiple holes is given by this. It is very similar to single hole shielding effectiveness. Only this factor is added, because over here we are having n number of holes. So n is nothing but the number of apertures that are there on the perforated shields. So this is for n holes and this is for a single hole.